Okay, welcome back to another video log recording session where I talk about genetic algorithms and whatever is related. I rant about it, I talk about it, mostly just ranting and going over the experiments that I ran. So, from in the previous video where it was where I covered this notebook, Genetic Algorithm Grid Search 3, 40 items, and also 50 items. We have seen this weird thing happen where the plot just peaks and then it falls and then plateaus outwards, the average of top 30 entities. And this happened regardless not regardless, but still, it did happen. And and with 50 items, the dip, the peak minus the plateau level, was bigger if we kept using the parent selection scheme and the mutation, which together I would just call the evolution policy. If we kept on using the same evolution policy, the more items, the fact that we had more items led to bigger dips. So in today's Jupyter notebooks, probably in this video I'll be covering 3 notebooks plus the one from before, so that's 4 in total, but 3 new ones where I go over what I have done to sort of control the dip, control the size of the dip, or control where or when it happens. But so let's get into it. So when we look at this, when we look at the dips here, we can only imagine, or I can only imagine, that the reason is that the best ones, the ones that were responsible for this peak, get faded out because they mutated and they went above the physical weight threshold, or the constraint variable, max constraint variable, and therefore they had to be struck out of the population. And when that happened, the other entities within that pool, in that generation, of course they have no idea what that entity or entities that got struck out were like, because they don't really share. But so maybe in the future I could build a sharing function, but that's not for now. Right now I'm trying to focus on how I can devise a more organic or natural way of natural form of evolution scheme, parent selection and mutation. So again, what I think happened here is that the ones responsible got struck out and they were gone, and then when they are gone, the next best ones get to procreate, and their information keeps getting passed on to later generations, and they become the dominant forms. They become the dominant archetype, and they just keep oscillating from here and on out to the right plateau outwards. So that's what happens, and when that happens, or while that is happening, there were no entities that were able to procreate and mutate to the peak level. There were some other ups and downs, there were some other ups, but never as high as the peak level. Even when there were even when population is at 2000, when population is set at 2000, it doesn't really recover. But something different might happen. We'll see. So naturally, what I can do first is alter the mutation level. That's number one. Or I did this separately. So alter the mutation level. The second thing I could try, or I did try, is make the parent selection scheme, or rather adopt a more generous parent selection scheme. And third is just a sheer population size, or just a bigger population size. So yeah. So here we go. First, low mutation rate. So here everything is the same. The items are the same. We still have the 40 items, 40 utility values, and 40 constraint values. However, in this notebook, the mutation rate has been set to 0.01. So they're going to mutate at a slower level, and this is what happened. We still see the peak, and then we still see the plateau, and it's still a huge dip. Well, I don't know about huge, but it's still, the dip is about the same size. However, because of the new lower mutation rate, in every evolution run, the populations peak a lot later than before. Here we go. See, before, when mutation was at 3%, the latest it peaked at it was before 50. Now it's after 50. The earliest is after 50, and then the latest is at around 125. So it doesn't actually do much other than just slow down the peak time. So that's what happens with low or lower mutation rate. And next up is a more generous parent selection scheme. This is when the weights at which the entities are chosen are computed by dividing the population size by, instead of 1, 3, 5, 7, 9, 11, and so on, but divided by 1, 2, 3, 4, 5, 6, 7. So the first entity with 500 populations, with 500 entities in the population, the first entity will have a weight of 500. The second will have 250 instead of 166. The third one will have 166 instead of 135, instead of 100, etc. So it's very this one's more generous. It's less competitive. And when we do that, we still have, this is with the lower mutation rate, this is with the more generous parent selection scheme. It's still the same dip. However, now we see that the dip is kind of smaller, but only because the peak is lower. But the peak still happens, the dip still happens. So we're still there. And of course, in this one, where the mutation rate is at 3%. So generally, what I did next is just a sheer bigger number in population. So I set the population to 3,000, and then I evolved it for 3,000 generations 10 times, and this is what happened. There's the peak, there's the plateau, and now we see that the dip is significantly smaller. It was at around, the dip was at around 18 to 20%, 18% let's say. Now it's at around 10%. So I can only guess, but I think it might be one of the things that happened here. I think I might be, quite accurate in saying that because the population is so big, some of the entities responsible for this peak survive. Not all of them die out. Not all of them just get struck out because of the weight threshold, but they survive, and then they pass on the information. But there is still some loss of information because now the dip is still here, but it's a lot smaller. Because now the plateau level is slightly above 900, whereas before it used to be around 800. So it's about 12% increase. But it's so what I think I can expect to see is that a bigger population than 3,000, for example 5,000, it might bring this even closer. But I think therein also lies an innate problem. And the problem is that the higher or the closer the summed utility value gets to the very best answer, the closer it gets to the weight threshold. So, given that, the best one, if it doesn't maintain itself, if it doesn't copy itself, the entities at around here, if something goes wrong, they're out because of the weight threshold. Sure, they could mutate to have a lower summed utility value and a lower summed constraint value or physical weight value, and they survive. But then, yeah, no problem. They survive to pass on the information, but otherwise they just disappear. So that's really hard. But a good thing is that at least I now know that a bigger population does tend to save some bit of the information, but also at a cost, because more population mean more computation. Yeah, this is what happened when it was at 2000, when population was at 2000. See, there's still some dip, 1000, and then still around 900, but kind of very oscillating. And here, this is slightly more than 900, and this is at 3000, this is at 2000. So from 2000 to 3000, that's 1.5 times more, or 50% increase in the population. But the information that got kept or maintained wasn't, I don't think it was 50% more. I think it was way less than that, way lower than that. So it's not all, I don't think it's a good idea to always increase the population, as in it's not really bang for buck. And also, if you think about it, now that I think about it, I have to be honest, top 30 of 500 is less than 10%. However, top 30 out of 3000 it's 1%. So I am only measuring the top 1% here, whereas here this is slightly more than top 1%, and when the population is 500 or 300, that's top 10%. So of course it's going to be lower. So I don't know if these are actually a fair comparison, but for now I think this is good enough just to see that these dips occur, and a bigger population does tend to mitigate the dip, minimize or control the dip. But yeah, I think I still have to I still have a lot of some things to try out, and I have tried them out, and I will make videos about it, video logs about it. But yeah, there's still a lot to uncover. So that's about it. TLDR, or conclusion: more population helps with the dip, but at a cost. Low mutation rate does not seem to help for now. And what's this? Yeah, and more generous parent selection doesn't seem to help for now. I mean, there will be ways where this can. I firmly believe that there can be ways that a more generous parent selection scheme can help with controlling the dip, or minimizing or eliminating the dip. Or maybe a dip isn't such a bad thing after all. Yeah, okay. That's about it. Or maybe I have something. Okay, more on that. A dip might not be such a bad thing after all, given that the problem or the conditions can change. But the fact that these can also change, or these may change, is not a problem if you see these entities as just solutions, as non-living beings. It's not a problem. You can just wipe everything out and restructure everything to account for all the changes in the problem set and all the conditions, all the new conditions. But since that is not what I'm doing, it's very important that I keep the population that have evolved or that have been evolving to that point, and apply the new conditions and new problem sets, and then evolve with that existing or pre-existing population and go on. I'm not again, because the purpose is not to generate solutions to a problem, strictly speaking. I'm actually talking about genes and genomes, and for that reason I think all parent selection schemes are of some use, even the dumb luck ones where everything is just done randomly, where every parent is just picked randomly, even the one where the top entity is replicated dozens of times, even the one where the parents are selected depending on how similar or not similar, dissimilar, is that a word? Dissimilar they are. Yeah, that's about it for this video. Thank you for watching. Goodbye.